Before I start section 4.3, let's review a function we talked about at the beginning of this chapter. The exponential function, f of x equals 2 to the x. Here is its graph. We can make a table of values just to verify these points that are here, x and y. So we did this before. We plugged in these numbers. And we got these values. Which corresponds to these points on the graph. 2, 4, 1, 2, 0, 1, 1, 1, negative 1, 1/2, negative 2, 1/4, negative 3, 1/8, etc. We know the domain of this function. It is all real numbers. And we also know the range. It is 0 to infinity. Well, we can also see that this is a one-to-one function. Because it passes the horizontal line test. There is no horizontal line that crosses this graph at more than one point. We also know that it does have a horizontal asymptote at y equals 0. The x-axis is a horizontal asymptote. Now, because this is a one-to-one function, we know that that means it has an inverse. And we can graph the inverse by drawing the line y equals x, and then flipping the graph of y equals 2 to the x over this line y equals x. Remember, when you graph the inverse and you flip over the line, all the coordinates switch. So the point 2, 4 on the new graph will be the point 4, 2. So this point flips over to this point. The point 1, 2 will get flipped over to the point 2, 1. The y-intercept 0, 1 will become the x-intercept 1, 0 on the new graph. The point negative 1, 1/2 will become the point 1/2, negative 1. Negative 2, 1/4 will become 1/4, negative 2, and then 1/8, negative 3. So here's what the graph of the inverse function would look like. We can make a table for this inverse function, f inverse of x. Write the ordered pairs that go along with it, which are just switching the input and output from our original function f. We also know that when you find the inverse, the domain and range switch. So the domain of f will become the range of f inverse. The range of f will become the domain of f inverse. Of course, this is also a one-to-one function, but now it has a vertical asymptote that is the y-axis. It's the line x equals 0. So this red graph represents the inverse of that blue graph, the function y equals 2 to the x. Let's use the four-step process to try to find an equation for the inverse function. Remember, first we start out by replacing f of x with y. Then we switch x and y. And then we try to solve for that y, isolate that y. Now, give it a couple of minutes. Pause the video. Try to solve that equation for y, so that y is on one side by itself and the other side is only a function of x. Actually, we haven't seen a function that would solve this equation for y so far in this class. That function that gets y by itself is this new function called the logarithm base 2 of x. So this is the equation for the inverse. It is log base 2 of x. So logarithm in base b is nothing other than the inverse of the function b to the x. So you already know some stuff about this function. You know its domain is 0 to infinity. You know its range is negative infinity to infinity. You know it has a vertical asymptote at the y-axis. And you know what the graph looks like. You also know some values for this function. Like if I just pick this last ordered pair here, we know that log base 2 of 4 equals 2. We know that log base 2 of 2 equals 1. That's what this ordered pair tells me. We know that log base 2 of 1 equals 0. And this one tells me when I plug in 1/2 for x, so log base 2 of 1/2 equals -1. So a logarithm in a base is really nothing other than that missing exponent. So to find log base 2 of 4, you ask yourself, oh, what should I raise 2 to get 4? The answer is 2. Here, what should I raise 2? Put a little question mark on top of that base there. 2 to what power gives me 2? The answer is 1. 2 to what power gives me 1? 2 to the 0th power gives you 1. 2 to what power gives me 1/2? 2 to the -1 power gives me 1/2. So this was just one specific example of looking at the exponential function 2 to the x. And we can see that it has an inverse. We tried to find its inverse. We couldn't. We needed a new function. That new function is called Logarithm Base 2. Let's do it now for any exponential function, b to the x, for any base, as long as, again, of course, b has to be positive and not equal to 1. So we officially start section 4.3, the study of logarithmic functions, by looking at the graph of f of x equals b to the x, and then seeing whether it's exponential growth or decay, it doesn't matter. This is what it would look like if b is bigger than 1. And remember, this is what it would look like if b is less than 1. No matter what, it's a one-to-one function. And it's going to have an inverse. And so what do we call that inverse? If you try to do the 4-step process here, you replace f of x with y, you switch x and y, and you try to solve for y, and what is that new function called? We call that log base b of x. So let's remember this. Log base b of x equal y is just another way of saying x equals b to the y, which is what it says right here in this box. We define the logarithmic function with base b to be a function such that b to the y equals x and log base b of x equal y are equivalent equations. They say the same things. They're just different ways of writing it. One of them has x on one side by itself. One of them has y on one side by itself. So that's just to say you can go back and forth between these two ways of saying the same thing. One is called logarithmic form and one is called exponential form. So here's a few examples of writing equations that are in one form and convert them into the other form. So if they're written in exponential form, like this first one, when you write it in logarithmic form, you keep the same base. So here the base is 4. We are going to write log base 4. And if you compare it with what this looks like, b to the y equals x, now it's 4 to the y equals x. This is the same as saying log base 4 of x equals y. One way some students find helpful to visualize, you always go like this. The base raised to that power equals what's inside the logarithm. And what's inside the logarithm, or a lot of other functions, we call them the same thing, is what we call the argument of the logarithm. So in this next one, we have another exponential function again. It says 2018 equals e to the 2x minus 1. So to translate that into logarithmic form, you write the logarithm log, and then always the base goes sort of at the tail of the G here. Write it down here. Don't write it next to it. The base is E. And then we're really just switching the input and output, because remember, they're really inverse functions. So here, the E had the input 2x minus 1. Now the input of the logarithm is the 2018. And on the other side, we have 2x minus 1. And you can double check that. See, e to the 2x minus 1 equals the argument, 2018. In the next problem, we have an equation written in logarithmic form. Log base 2 of x equals 3. We want to write its equivalent exponential form. So the base stays the same. 2 to the third power equals the argument. So we write 2 to the third power equals x. You don't have to do anything with this. It just says write it in equivalent form. For the next one, it's in log form again, and we want to write it in exponential form. The base is 14. And here, instead of having the log equal to something, like you see up here and like you see in this example, it's something equals the log. So if it helps you visually, put it on this side, equals x. And then we can use that visual again. The base raised to that power equals the argument. So we get 14 to the power x equals t plus 9. And so here's what you would have in general. If you have logs in some base of some stuff equals whatever, some other stuff, the way you rewrite this in exponential form, the base stays the same base in both forms, but then you write that to that power equals the argument there. So we get the base raised to the power whatever equals the stuff. So you'll practice in homework going back and forth between logarithmic form and exponential form of an equation. Remember that they are equivalent ways of saying the same thing. And also remember that the logarithm is just the inverse of an exponential function. To simplify logarithmic expressions, you need to understand the definition of a logarithm, which really can be thought of as the missing power. What's the power that gives you what we have inside the logarithm, that gives you the argument? You also have to review your properties of exponents. So let's pause for a second and go through some properties of exponents and definitions. Here's a file that gives you an overview of some properties that you should remember about exponents. You can find this file also in Canvas. We start out by reminding you that a to the n just means repeated multiplication as long as if n is a counting number. So a to the third means 3 copies of a being multiplied, and so on. And because of that definition, we have all of these properties. They just come from properties of multiplication and division. So if you have the same base raised to 2 different powers, or even the same power, when you multiply them, you add the exponents. You write the base once and you add the exponents. When you divide, you subtract top minus the bottom exponent. You can distribute a power outside parentheses to all the factors inside. This only works if you have multiplication or division inside the parentheses that get raised to the power. And then here we have a power of a power. Then you multiply the powers. So these come from that definition that says if n is a counting number, then it's really just repeated multiplication. But actually, we can extend these to even when the n, the power, is not a counting number. Even if it's an integer or a rational number, we still have all of those same properties in place. But you might want to remember what are the definitions of, and we've worked with these already a little bit at the beginning of chapter 4. So anything to the 0th power except 0. But any non-zero number to the 0th power is 1. Negative exponent basically just means reciprocal, 1 over. If you have a negative exponent on the bottom, it's like you can bring it to the top and drop the negative. If you have a negative exponent on top of a fraction, it means just write the reciprocal of that fraction and make the exponent positive. Then we have fractional or rational exponent. Basically, they just mean a root. So a to the 1 over n just means nth root of a. A to the m over n means you do nth root of a. The number on the bottom is the root, just like I say, like in a tree, the root is on the bottom. That gives you the root, which we also call the index, the little number inside the radical here. And then the power, you can either write inside the radical or you can find the nth root first and then do the power outside, depending on which one's easier to do. Of course, we always have to worry about what happens if you have an even root with a negative number inside. That's not going to be a real number. So we say if n is even, then nth root of a is only real if a is not negative, if it's 0 or positive. Same thing with this next property. So in this file, you are going to see a few examples that remind you how you can simplify expressions with exponents, and then also how to evaluate expressions with a rational exponent, and how to simplify expressions like this, where you have, when you can rewrite this cube root of x squared can be written as x to the 2/3, and square root of x can be written as x to the 1/2. And then we have that property that says when you're dividing, you write the base and you subtract the exponent, and you do your arithmetic of fractions, and you get the answer, x to the 1/6, which can also be written as 6th root of x. Then you are also asked to try to find these numbers without a calculator first. 81 to the 1/4 basically just means 4th root of 81. What number to the 4th power gives you 81? And that number is 3. The answers are down here, but you should try to do these on your own first, and you can also check on your calculator, and then you can check the answers here. So make sure you review your properties of exponents that are going to be important in the next couple of sections. So back from our detour, we want to evaluate these expressions, just understanding the meaning of logarithms and knowing our properties of exponents. Now here are some that maybe you feel like you need to memorize, but you don't have to think of it as memorizing if you understand what the expression means. Log base b of b, to find that you have to ask yourself, b to what power would give us b? Well, the answer is 1. With the next one, we have log base b of 1. To get the value of that, you have to ask yourself, b to what power gives you 1? And remember, b to the 0th power gives you 1. And then this one is just sort of one of those things where the answer is in the question. To get the value of log base b of b to the x, you have to answer b to what power gives you b to the x power. Well, look at that. The b's are matching, so what should the question mark be? It's just x. Let's just do some of these problems evaluating the expression, and you want to try to do this without a calculator. Again, remember, to find the value, it's really like having a question mark on top of that base there. 2 to what power gives you 8? And you have to write the answer. So this is the work that shows how you get the answer. But the answer for this is 3, because 2 to the 3rd power gives you 8. For this one, you have to ask 2 to what power gives you 1 over 8? Okay, 1 over 8, I know that 2 to the 3rd power gives me 8. 1 over 8 is the reciprocal, so that means the power must be negative. Try to do the next few on your own before you check the answer. Pause the video and do these problems. So for this next one, you have to find out, okay, 2 to what power gives me square root of 2. And this is where you have to review those rational exponents. You know that square root means 1/2 power. So 2 to the 1/2 power gives you square root of 2. This one is just like this property up here, which says because the exponential and logarithm are inverses of each other, and you might remember from when we studied inverse functions, when you apply f and then f inverse to an input, you get the same input back. Or you can just think of this one as 2 to what power gives me 2 to the 100th power. It's like saying, what's the name of that woman called Sherry? The answer is in the question. 2 to what power is 2 to the 100th power? So the power, the missing power, is 100. Now this one might be a little bit trickier to explain that way, but you can just think of it as here, it's applying inverse functions one after the other. So log base 2 of 2018 by definition is the power you would put on 2 to get 2018. This number that I'm going to cover up now, remember what was inside it. It was log base 2 of 2018. By definition, this is the number that when you put on top of 2, you get 2018. Well, now I'm putting it on top of 2. What should I get? 2018. You can also think of it as we find log base 2 of 2018 and then put it on top of 2, the inverse function. So that just gives us the original input back. Whoops. Don't know why I erased that. Now for this next one, you have to answer the question 2 to what power gives you 1 over cube root of 2. Well, you have to find a way to write 1 over cube root of 2 as a power of 2. I know that cube root of 2 can be written as 2 to the 1/3. So 1 over cube root of 2 is 2 to the negative 1/3, which means the answer to this is that missing exponent, which is negative 1/3. So you really have to practice your properties of exponents to be able to do some of these problems. If you look at your calculator buttons, you will see that there are 2 logarithm buttons there. One of them just says log of x, so it has the log for logarithm, but there's no base. Then the understanding is that it's log base 10, and that is called the common logarithm. Then there's another button that you see on the left of your calculator. It doesn't say log, it says ln. ln of x is another special case of a logarithm. It's log base e. Remember that number e, the famous natural number. So this is called the natural logarithm. Instead of writing log base e, we just write ln. So you can just plug these numbers into your calculator to get their values. So to find ln of 10, you just press the ln button. Then it automatically opens parentheses, and then you type 10, and it gives you the approximation for that. So to 5 decimal places, that would be 2.30, and so if I count 5 decimal places, I get to the 8 here. The next digit is 5, which means I need to round that 8 to 9. You round up if the next digit is 5 or bigger. Log of 40, you then press the log button and then type 40, and that gives you this number, 1.60205. The next digit is 9, which means we have to round up, and we get 1.60206. So remember that we use this symbol that means approximately equal to when you're writing an approximation. If you're asked for an exact answer, you do a problem and the answer is ln of 10. The exact answer is ln of 10. The approximation is this number. So you should remember what the graph of basic logarithmic functions look like. They're just inverses of your basic exponential functions. So here we are given the graph of y equals log base b of x, and really the only thing we have to find is that base. But I know that it goes through the point 9,2. We did this exactly the same way with the exponential function. I mean, I know that if I plug in 9 for x, I get 2 for y. So let's plug them in. And so basically we have to find this value of value of b. I'm going to rewrite this equation in exponential form. And if it helps you, instead of having the 2 equals here, you can write it here, because some people are just used to that visual with the base to that power equals that argument. So this gives us b squared equals 9. Well, technically, this equation has 2 solutions, plus or minus 3, but just like with the exponential function that we said the base can't be negative, it has to be 0 or bigger. It has to be bigger than 0 and not equal to 1, so we can't accept the negative. B must be 3. So the equation of this function is log base 3 of x. And so we are given, actually, the graph of y equals log base 3 of x again in this next problem. And every time we learn about a new function, we want to learn about its properties, its domain and range, its graph, and then graph its transformations. So here's the graph of log base 3 of x, which makes sense. It goes through 1, 0, it goes through 3, 1, it goes through 9, 2, and then this point would be 1/3, -1 right there. It does approach. It looks like it's hitting the y-axis, but it actually doesn't. It just gets closer and closer to it. That's a vertical asymptote right there. Now we want to graph this transformation. So we follow the steps. This one says that I have to shift left 3 units. Then the negative says we have to flip over the x-axis. And then the +1 says we have to shift up 1 unit. So you want to maintain this shape. The shape doesn't really change, but it translates right, left, up, down, and then flips. And so you can just take those key points that we have here and see where they go. So when you shift 3 units to the left, the point 1, 0 is going to go 1, 2, 3 over here, and then flip over the x-axis, it stays there, and then up 1 unit, it ends up over there. Then the point 3, 1 goes 3 units to the left, flip over the x-axis, and then up 1 unit, so it goes over there. Then the point 9, 2 goes 3 units to the left, flip over the y-axis, and then up 1 unit. The vertical asymptote goes 3 units to the left, 1, 2, 3, and flip over the x-axis. It still stays the same vertical line, and then up 1 unit, it still stays the same vertical line. So then what does the graph look like? This one was going down and getting close to the vertical asymptote, but we flipped it over the x-axis, so this one's going to go up and get closer and closer to the vertical asymptote. And so it's going to basically have this shape. So we do the same kinds of transformations that we did before to any function. Now you have to know the basic graph of logarithmic functions and be able to graph their transformations. So remember that we opened this lesson by looking at the graph of b to the x and looking at its domain and range, and then realizing that the logarithmic function is just the inverse of that, so the domain and range got switched. So that means when you are looking at the graph of y equals log base b of x, whatever this x is, whatever the inside is, see, it has to go 0 to infinity. So that has to be bigger than 0. So if instead of x you have some other stuff, then that stuff must be bigger than 0. So to find the domain of a logarithmic function, we know that the inside the log, remember we call that the argument, whatever is inside that argument, just copy that and set that greater than 0. So here I see what's inside is 8 minus 2x, so I will copy that and then write greater than 0 to find the domain. Now, for all of these problems, then you're going to end up having to find the solution to an inequality. If it's linear, you do one thing. If it's rational, you do something else. Polynomial, whatever it is, do what you need to solve the inequality. So for linear, we'll just do the same thing as the equation. We'll try to isolate, but remembering that if I divide by a negative or multiply like I do here, I have to flip that inequality symbol. So the solution to this inequality is x less than 4, which means the domain of this function is negative infinity to 4. For the next problem, there's two things we have to consider, because remember when you have two functions, and in this case we're subtracting these two functions, the radical and the logarithmic function, then we have to find the domain of each and then find the intersection. For a square root function, I know that the inside has to be greater than or equal to 0. And for the logarithm, it doesn't matter what the base is. In this case, the base is e. Then 10 minus x has to be strictly bigger than 0. So let's just solve each of these inequalities, and then we have to find the intersection of their solution sets. For this one, I will subtract 2, divide by a negative, which flips the inequality. For this one, I will subtract 10, divide by a negative, which flips the inequality. And remember, we want the intersection, and. So if I put these two sets on the number line, let's say here's 0, here's 2, 3, 4, 5, 6, 7, 8, 9, 10. X less than or equal to 2 is this set. And I'll do the other one a different color. X less than 10, remember that means I have a hole at 10, is this set. The intersection is where you see both blue and red. So in this case, x has to be less than or equal to 2. So the domain of this function is negative infinity to 2. Here's another example where we have to find the domain. There's a couple of things going on here. We are now dividing two functions, the logarithmic function and x plus 1. And remember, when you divide, you want the intersection of the domains of the two functions, and also you don't want the bottom to become 0. So for the top function, I need to set whatever's inside the logarithm strictly bigger than 0. 0 itself is not okay, unlike square root functions that could take 0 and positive. Logarithms can only take on positive values. And then also, we don't want the bottom to be 0, so x plus 1 cannot be 0, which means x cannot equal negative 1. We want the intersection of these two sets, the solutions to these. Now for this inequality, you might be tempted to isolate the x squared, but that's not how we solve these polynomial inequalities. You have to factor. So you get 2 plus x, 2 minus x, greater than 0. And for that, remember, we can make a sign chart. Now we can do it pretty quickly. Key numbers there are negative 2 and 2. The sign starts out negative out here because the leading term is negative x squared. And then they're all just to the first power, so you switch all the signs. So greater than 0 happens here. But we can't have x equal to negative 1. And so negative 1 must be taken out of that set because of that condition. So the intersection of these two things happening, we want both of those things being satisfied. Then the domain is going to be -2 to -1, open, that's -1 right there, union -1 to 2, all open. Let's look at a quick application of logarithmic functions. The age of an old artifact can be measured using a method called carbon dating, where the amount of carbon-14 is measured. If D, we call this D sub 0, or sometimes you hear it called D naught, is the original amount of carbon-14, and D is the amount currently remaining, the age of the artifact is given by this function. Find the age of an artifact that has 68% of its original carbon-14 left. So it starts out with the original amount is D naught or D sub 0, and what's left, which we are calling D, is 68% of, that means 0.68, and a percent of, you always multiply, times its original, which is D sub 0. So I can go to that formula that they gave us, and I can plug in 0.68 D sub 0 for D, and then copy everything else. So I copied everything in the formula. I just replaced D with what it's equal to. Well, these are going to cancel, so now this is just a calculator problem. So you just plug this number in to your calculator. And we get approximately 3,188, and I would just round it to the nearest year, because when we're talking about thousands of years, who cares about 0.2 or 0.3 years? So this is the age of the artifact.